Okay, so our session's being recorded now. So you learned about section 8.6, where you could take a function, certain kinds of functions, like rational functions, um, arctangent function, the log function. These special functions, you were able to rewrite those functions as power series. And the functions are equivalent to the power series over an interval of convergence. And you had to identify the interval of convergence as well for your power, for some of your power series. And that's nice, but the approach of section 8.6 is dependent on the fact that you were to take the rational function 1 over 1 minus x and express it as a geometric power series. And then you could adapt that formula to different rational functions by adjusting your common ratio r. Yeah, that's fine. That's good. But we do need a more general approach for being able to take a function and writing it as a power series. Because, for instance, like the cosine function, if you wanted to write the cosine of x as a power series, you can't, section 8.6 would not be helpful. If you wanted to write the exponential function, e to the x, as a power series, section 8.6 would not be really convenient. Okay, so the Taylor and Maclaurin series in section 8.7 are an approach developed by Brooke Taylor. He lived from 1685 to 1731, and Colin Maclaurin, who lived from 1698 to 1746. It's a technique that allows you to take any function that is differentiable, meaning it has, you can take any number of derivatives, a differentiable function, and write the differentiable function as a power series. So how does this work? How does this work? Well, let me go ahead here and start here that we suppose that any function can be represented by a power series in this form. Okay, so this here is the form of a power series. I mean, a power series, is you've dealt with power series from section 8.5 and 8.6, and you know that the power series take on this form. And the a is a number that could be 0, it could be equal to a different number, it all depends. But we're assuming that any function f of x can be written as a power series. Now, of course, the coefficients c sub 0, c sub 1, c sub 2, c sub 3, and so forth, those coefficients are going to be dependent on what? They're going to be dependent on what your function is, right? And so, I mean, that would make sense. So let's see if we can come up with a way to find these coefficients, c sub 0, c sub 1, c sub 2, c sub 3, and so forth. Well, what they suggest is let's try to determine what the coefficients are. To begin, they say, all right, hold on here. Yeah, to begin, they say let's let x equals a and put it in this equation 1. Well, if x equals a, all of the terms are going to drop out, right? Because a minus a is 0. The third term, the second term, if you put a in for x, you're going to have c1 times a minus a. That's c1 times 0, that's 0. The third term is c2 times x minus a squared, right? Well, if you put x equals a in there, you're going to get c2 times 0 squared. That's going to be 0. So when you let x equals a, all the terms drop out except c sub 0. That means that c sub 0 is equal to your function evaluated at a number a. So we have a formula now for c sub 0. Okay. Are there any questions so far? Are there any questions so far with what we're doing here? Okay. Okay. Well, then let us continue here. One moment here. Gotta find the right thing. Okay. So now, well, the next coefficient is C1. All right. But what we're going to do is we're going to differentiate the terms in equation 1, the terms right here in that equation. We're going to take the derivative of f. That's going to give us f prime of x. Okay, now f prime of x, well, if we differentiate this f of x here in the pink, the derivative of a constant is 0. The derivative of x minus a is 1. The derivative of x minus a quantity squared would be 2 times x minus a. And derivative of x, the fourth term, x minus a cubed, would be 3 times x minus a squared. And what's going to happen is you're going to get this formula here for your first derivative. Okay, so it's easy to differentiate a polynomial. I mean, this is really more than a polynomial. It's an infinite, it's a power series, but it's like differentiating a polynomial. Easy to do. Now what are we going to do? Well, we want to determine what C1 is. So what are we going to substitute in our first derivative, f prime of x? What are we going to substitute in for x to determine that C1 coefficient? What do you think we're going to substitute in for x? If we want all the terms to cancel on the right side, except for C1, I'm looking at that equation 2 there, f prime of x. If we want all the terms to drop out, to become 0, except for C1, what would we let x equal to? What would we substitute in for x? What value? Well, what's the only value of x that would make x minus a equal to 0? What's the only value of x that would make x minus a equal to 0? That's right, Michael. A. X equals a. Okay, well then we're going to let x equals a. And if we do that, all the terms in equation 2 drop out, and it turns out f prime of a will equal C1. That's what it'll equal. So now you've determined, now you know what C sub 0 is. You have a formula for that. C sub 0 equals f of a. C sub 1 equals f prime of a. Okay. Well, all right. Next, we have to find out what C2 is. So what are we going to do to equation 2? If we want to find out what C2 is, what do we have to do with equation 2? What are we going to do with that equation? We're going to take its, what? We're going to take its, it's a D word I'm looking for. That's right, Kahindi. Good. We're going to take its derivative. We're going to take its derivative. And if we do that, then here's f double prime of x. Right here. Here it is. And we want to solve for C2, so I'm going to let x equals a. I'm going to substitute x equals a in equation 3 here. And the result is going to be that f double prime of a equals 2C2. So C2 will equal F double prime of A over 2. Right? That's going to be your next formula here. Okay, so we just kind of highlight here. All right, and we can go one more step here, right? We can go one more step. Let's take the derivative again. Here's the third derivative of f. Okay, here it is. Equation 4. We'll substitute in x equals a. Right? We'll substitute that in equation 4. And it turns out that then the third derivative of f evaluated at a equals 2 times 3c3 equals 3 factorial times c3. Okay, so interesting, right? Interesting. So c3 is going to equal the third derivative of a divided by 3 factorial. C2, by the way, is the second derivative of a divided by 2 factorial. C1 is the first derivative of the, I'm sorry, I'm not saying this right. C3 is the third derivative of the function evaluated at a divided by 3 factorial. C2 is the second derivative of the function evaluated at a divided by 2, or 2 factorial. C1 is just the first derivative of the function evaluated at a, but that can be thought of as f prime of a over 1 factorial, because 1 factorial equals 1. And so there's a pattern. There's a pattern here. There is a pattern. And this is the pattern. The nth derivative of the function evaluated at a is equal to n factorial times that coefficient c sub n. And so therefore, c sub n equals the nth coefficient in this power series, this general approach we're taking. The nth coefficient is going to equal the nth derivative of the function evaluated at a divided by n factorial. So now we have then this result. We have this result, this theorem. If you can write a function as a power series, as they show you here in Theorem 5, the coefficients are given by the c sub n equals the nth derivative of the function evaluated at a divided by n factorial. And so you see, in order for this to work, the function has to be differentiable. Okay. And so then here's the general formula. If we want to take a function that's infinitely differentiable and express it as a power series, it would be this power series that you see in equation 6. This is called a Taylor series of a function at x equals a. That's what that's called, a Taylor series of a function at a. Now the a has to be, or a Taylor series of a function centered at a. And the a has to be given to you, but of course, the a value, oftentimes you will pick that a value depending on the application. Okay, so are there any questions so far with this? Are there any questions so far? This is like a very important moment in your life, the fact that you're learning this piece of information. This is used in many, many, many math courses that you'll be taking, and you'll see it in engineering too. Statistics, you'll see it. It's used in all over. It's used in all the sciences. Because what you're able to do, you see, is you're able to take a function f of x, which could be a complicated function, and you're able to express it as the power series, which the terms are like terms from a polynomial. It's easy to deal with a polynomial. So that's the beauty behind this. And sometimes we let a equal 0. Okay, sometimes we let a equal 0. And if we let a equal 0, the Taylor series becomes what's called the Maclaurin series. The Maclaurin series is given here. And it arises frequently enough that it has a special name called Maclaurin series. Okay. Now, this, I want to caution you, that that the function will equal its power series only over an interval of convergence. Only over an interval of convergence. And that's why up here, when you first learned about the Taylor series, they have this piece of information right here. I guess hold on. I can remove the highlight. Hold on. Well, I got to have it all, I guess. The absolute value of x minus a is less than r, which is your radius of convergence. I mean, again, a power series, a function that equals its power series only over its interval of convergence. But for many of the very common functions that you'll see, the interval of convergence might be all real numbers. Okay, so that being said, let's look at an example here. Let's look at an example, example 1. Well, first, are there any questions so far? Are there any questions so far? All right. Example 1 says find the Maclaurin series of the function f of x equals e to the x and find its radius of convergence. So, well, okay. And the books always start off with this one. F of x equals e to the x. All the derivatives of e to the x are e to the x. So that means the terms of the Maclaurin series, the coefficients, well, I want to be a little bit careful. The Maclaurin series, we have to evaluate the derivatives of the function at a equals 0. Well, all those derivatives are going to equal 1. And so the Maclaurin series for e to the x, if we use the Maclaurin series formula, okay, the Maclaurin series is just what you see here. The Maclaurin series for e to the x is equal to the sum where n goes from 0 to infinity of x to the nth power over n factorial, which if we write out a few terms of the series, that'll be 1 plus x over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial, and so forth. Okay. Are there any? And we'll do a few problems too. You know, we're looking at some book examples. The book has nice examples, but we're going to look at a few problems as well here. Are there any questions so far? All right. Well, now the radius of convergence. To get the radius of convergence, you're going to use, we have a power series, and you use the ratio test to get the radius of convergence. So you know how to use the ratio test. You take the ratio of the n plus first term of the power series and divide it by the previous nth term of the power series. And if you do that in this case, that ratio is going to reduce to the absolute value of x over n plus 1. And that, as n gets large, as n goes to infinity, that ratio approaches 0, which is always less than 1. So by the ratio test, this series converges for all of x, and the radius of convergence is r equals infinity. Okay, are there any questions at all on this before we move forward? Okay, who's feeling a little bit comfortable? Who's feeling reasonably comfortable so far? Well, okay, Michael is all right. And I'm just waiting for responses, right? Thank you, Michael. Michael's okay. All right, good. Okay, well then let us proceed on. Let us proceed on. So this exponential function, you have the power series here, 1 for the e to the x, which is 1 plus x squared over 2 factorial plus x cubed over 3 factorial. And what they do here in figure 1 is they draw the e to the x power, okay, in red. That's the red function. And they've drawn what are called some Taylor polynomials. Okay, they've drawn some Taylor polynomials. Okay, so the first Taylor polynomial, okay, first degree Taylor polynomial, t sub 1 of x, is 1 plus x. Those are the first two terms of the power series for the exponential function e to the x. Okay, the t sub 2x is the second degree Taylor polynomial. That's 1 plus x squared over 2 factorial. The third degree Taylor polynomial, t sub 3 of x, is 1 plus x squared over 2 factorial plus x cubed over 3 factorial. Okay, and they've drawn these three Taylor polynomials along with an exponential function e to the x in figure 1. Okay. So what can you tell me about, I mean, which Taylor polynomial? So of course, it's a the Taylor polynomials are based off the Maclaurin series, and the Maclaurin series was centered at a equals 0. Okay, look at the exponential function in red and look at your three Taylor polynomials and tell me which one does the best job in approximating e to the x, the exponential function, over like over the widest domain. Which Taylor polynomial is the best? The first Taylor polynomial T1, the second Taylor polynomial T2, or the third Taylor polynomial T3? Which does the best job? Okay, that's right, Michael. T sub 3, the third degree Taylor polynomial. Why would that do the best job, you think? Why would that do the best job? I mean, of course, it doesn't. Eventually, the third degree Taylor polynomial, that cubic polynomial, will look different from the exponential function as you move away from, x equals 0. As you move away, the polynomial will get, it'll get worse. The approximation will get like worse, right? But it does okay over a reasonable amount, reasonable domain around x equals a reasonable range of x values, I guess I should say. But why would T3 do the best? Why would T3, the third degree Taylor polynomial, approximate the exponential function e to the x better than t sub 2x or t sub 1x? Why would that be the case? Okay, so let me see. Michael says closest to the original after a. Yes, that's true, and you can pictorially see it. But why? You're right. Looking at the picture, T3 does approximate the exponential function the best. Would we expect it to do the best? I mean, is it just coincidence? Why do you think? Is there a reason why maybe T3 approximates e to the x better than T2 or T1? Good. That's right. More terms. More terms. Okay, so keep in mind here that the exponential function e to the x is equivalent to this infinite series, this power series with an infinite number of terms. So of course, the more terms you take of the power series, the better that polynomial would approximate the exponential function. It would approximate it better over a wider range of x values. Okay, so I just wanted to bring that to your attention. All right, now something else. Are there any questions on that? Okay, well, let me bring something else to your attention here. We're not going to worry about the Taylor remainder formula until section 8.8. But in the textbook, there is a table. Here, I'll find it. Important Maclaurin series and their radii of convergence. Okay. I clicked on it so you can get an enlarged view. You just make sure that you're seeing everything well here. Okay. So look at these functions. So the 1 over 1 minus x, the first function, well, you learn that expansion, that power series you learned from section 8.6. But they have the exponential function, the sine function, the cosine function, the arctangent, and the log function. You learn the arctangent and the log of 1 plus x in section 8.6. But you see, you can take many functions and write them as that functions that are differentiable, okay, that have derivatives. You can take many functions and express them as power series. And notice, like for e to the x, this is table 1 from section 8.7. And you're going to be referring to this table sometimes for some of your homework problems in WebAssign. But look on the right, like e to the x, they have the power series for e to the x, and then they have r equals infinity. The radius of convergence equals infinity. If the radius of convergence equals infinity, what's that tell you about your interval of convergence? If the radius of convergence equals infinity, what would the interval of convergence be? Okay, so I think, Michael, you mean all real numbers? That's right. That's right. And the sine and the cosine, the power series there, the Maclaurin series, which they can be derived, also have a radius of convergence or interval of convergence that's infinite. Okay, so if we go to, let me go to example 4 here in the book. I want to look at the and then we'll get to some problems, but we're not going to worry about binomial series. We're not going to worry about that for this class. But example 4 talks about find the Maclaurin series for the sine of x and prove that it represents the sine of x for all x. So here in example 4, what you do is you have the function sine of x, and you're going to take some derivatives. You're going to take enough derivatives so you can evaluate some terms, because you need to if you're going to try to find the Maclaurin series. So there's f of x equals sine of x, and the first 4 derivatives of the sine of x. And then to the right are the values of those derivatives at a equals 0. And so then what you do is you substitute in the values in the Maclaurin series below. The values of the function and its derivatives at a equals 0. And you're going to get, I want to be careful here, you're going to get here that you're going to get for the Maclaurin series x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th power over 7 factorial plus and so forth. And so the even terms drop out because the derivatives that go with the even powers of x equals 0. You can see that above, looking at, f of 0, f double prime of 0, and the fourth derivative of f at 0. But you end up getting then for your Maclaurin series, x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial and so forth. And that can be expressed then as the series where n equals 0 to infinity of negative 1 to the nth power, because it's an alternating series, times x to the 2n plus first power divided by 2n plus 1 factorial. Okay, so oftentimes what you have to do, if you want to find a Maclaurin series for a function, you have to write out enough terms so that you can figure out the series. Okay, so you can figure out the series. Okay, are there any and so, and then of course the radius of convergence, they can you could use the ratio test. You would use the ratio test. You could show the radius of convergence for this power series, or the interval of convergence is from negative infinity to infinity. Okay, so are there any questions before we move to some of my examples? Okay, and I mean, I hope it's more than, well, yeah, I mean, I think a lot of you are here. You're a little shy in answering, but please feel free to offer any input when I ask questions. Even if you're wrong, don't worry, we won't make fun of you, right? That's not what we're about here. You're learning. Okay, well, if there are no questions, then let me go ahead. Let's go ahead and do some examples here, some Dr. Duty examples. Okay, so okay, let me give you a moment to copy this example down, okay? Okay, so here we want to find the Maclaurin series for this function and its interval of convergence. Okay, so the cosine of 3x over 4. All right, so what do we have to do to construct the Maclaurin series for this function? What do we have to do? What's the first step? So that's right, Michael. We have to write out the formula, but to find the coefficients in the formula, what do we need to compute? What do we need to compute? We're in calculus. We need to compute the functions. What? It begins with a D. Derivatives. That's right. Very good. Okay. So that's what we'll do. That's what we'll do here. So let me give you a moment to copy down. Now, I don't think I need to read piece by piece what's going on, what I did here, but the function was the cosine of 3x over 4. The first derivative, we have to remember the chain rule, would be negative 3 times the sine of 3x over 4. The second derivative would be negative 9 times the cosine of 3x over 4. And I decide to compute 4 derivatives, and then I evaluate the 4 derivatives at a equals 0 because I'm looking for a Maclaurin series. Okay, so let me give you a moment just to copy that down. Let me know if you have any questions. Okay, all right. So now what we do is these values here Okay, all of them, right? We're going to take the values and substitute them in the Maclaurin series formula. That's what I've done here. So it turns out that I have three, well, hold on. Well, all right, this is what I have. And we really could use another term. We could really use another term. I can tell you that the sixth derivative of this function evaluated at 0, and you can you know, do this yourself. You can show, of course, you'd have to take the fifth derivative before you get to the sixth derivative, but you could show that the sixth derivative of this function evaluated at a equals 0 is going to equal negative. Well, I mean, looking at the coefficients here, I mean, let's look at what we got here. We have the f of 0 and the derivative of f of 0, the derivative of f evaluated at 0, f and its derivatives. The denominator seems to be always 4, right? But look at the numerators. The numerator went from, let's see here, we have a 1. We have it's a negative 9, but the point, we know it's an alternating series, but we have a 1, we have a 9, we have an 81. So I'm looking at the non-zero coefficients. What do you think? What do you think the next? I mean, for the next non-zero term. Okay, we know it's going to be, since the terms are going positive, negative, the fourth non-zero term would have to be negative. There would have to be a 4 in the denominator. What do you think is going to be in the numerator? What do you think is going to be in the numerator? That's right. Good, Michael. 729. Okay, because 1, you think of it like this. 1 is the same as 9 to the 0th power, right? 9 is the same as 9 to the 1st power. 81 is the same as 9 to the 2nd power. And 729 would be the same as 9 to the 4th power. Okay, so you have, once you detect the pattern, you can figure out the coefficients. Are there any questions before I move to the next page? All right. Well, all right. So we're putting in the values in our Maclaurin formula, Maclaurin series formula. And, you know, I've added a little bit of, just a little bit of context for you. Okay, here. And then we go to the next page. And I've now, what I've done is, well, I've rewritten the series, but I just added that that's additional term. Okay, and then what I do, so the first step here is basically a repeat of what you saw on the previous page. I just rewrote down the series. But then what I do in the next step is I rewrite the terms of the series, the coefficients of the series. And once you have enough terms of the series, hopefully then you can get the pattern. And it turns out this is going to be, this here is going to be the power series for our function cosine of 3 of x over 4. It is going to be the power series. And in fact, it's going to be for all real numbers. The interval of convergence can be shown to be equal to all real numbers. I'll show that in a minute, but okay. So hopefully by looking at the terms here of your power series, hopefully 4 non-zero terms was enough so you could come up with the formula. And this is how WebAssign is going to work for some of the questions. They're going to have like a multiple choice part where they give you different power series formulas, and you have to choose the right one that goes with your function. So you do have to be careful, because if you have 5 choices, you only have 2 tries, right? So you just have to be careful. Now, one thing I'll comment here, the negative 1 to the nth power, that should be obvious because you have an alternating series. You have always a 4 in the denominator, and then you have even factorial, so that would be 2n quantity factorial. The powers of x are even, you know, x squared, x to the 4th, x to the 6th, so that's x to the 2n. But here I have 3 to the 2nth power. I thought we were working with the 9. Well, 3 to the 2nth power is the same as 3, maybe I'll make that a little bigger. That's the same as 3 squared raised to the nth power and that's just 9 to the nth power. Okay? But I wrote 9 to the nth power as 3 to the 2nth power because I know, like in WebAssign, you might get a legitimate formula for your power series, but you don't see it maybe listed in the choices. Well, sometimes you have to rewrite the coefficients. I mean, 9 to the nth power is equivalent to 3 to the 2nth power. They're equivalent. Okay, so I just wanted to, you know, help you recognize that. Are there any questions? Okay, well now, this is true, but for what x values is this true? Okay, we have our Maclaurin series here, Maclaurin power series for the cosine of 3x divided by 4, but for what x values is this true? To answer this, you have to find the interval of convergence using the ratio test. And you will see, well, I'll show you the ratio test for this. Okay, I'll give you a moment to finish copying. Okay, let's go to the next page then if we're good. Let's use the ratio test on this power series to determine the interval of convergence. So you've done this many times. The nth term is going to be equal to the term of the power series. And you're going to take the ratio of the n plus first term to the nth term. Okay. And then you will get down to this step here. Let me give you a moment to catch up here. Let me know if you have any questions on what you're seeing here. Okay, so now what I do, as I've shown you, I group like terms together. But where students sometimes have difficulty is with the factorials. You have the quantity 2n plus 2 factorial and in the denominator, and then you have the quantity 2n factorial. How do you reduce that? Well, 2n plus 2, the quantity 2n plus 2 factorial, can be written as 2n plus 2 times 2n plus 1 times the quantity 2n factorial. By doing that, this allows you to reduce, to simplify, and then this is what you have left. But the absolute value of -1 times 3 squared over 1 over 2n plus 2, 2n times 2n plus 1 times x squared, that can be, x squared is always positive. So you can rewrite that ratio like this. You can drop the absolute value because x squared for any x value is always positive. And so as n gets large, this ratio is going to go to infinity for any x value. And so therefore, since that's the case, the interval of convergence is going to be all real numbers, negative infinity to infinity. Okay, are there any questions on this, what you're seeing here? It's not the, I mean, you know, the newer part of the problem is finding the Maclaurin series. That's the newer part of the problem that you're learning. The ratio test you've done, but I wanted to do one where you dealt with factorials. Are there any questions before I go to the next page? Okay, well, then we sum this up here. We sum that up that way. So the interval of convergence is for our power series is negative infinity to infinity, which again, that means the cosine of 3x divided by 4 is going to equal its infinite power series, that Maclaurin series, for all values of x. The radius of convergence is r equals infinity. Okay, then let's move on to a new example. If there are no questions, I'm going to let this be our next example. Okay. All right, an integral problem. So you've already seen how power series can be useful in computing integrals when we don't know the antiderivatives. Okay, here's another example. So let me give you a moment to copy the example down. How many of you like these Maclaurin series and Taylor series? How many think they're kind of cool? Now we're focusing on Maclaurin series. I should mention we're focusing on Maclaurin series. Let's see here. I'm just looking at the textbook. The example 7 in the textbook deals with writing the sine of x as the sum of a Taylor series centered at a equals pi over 3. Okay, so that's an example of a Taylor series. Maybe we'll look at that next. Maybe we'll take a look at that next. But let me give you a moment to copy this. All right, so, well, we are looking for a definite integral here. So for the function, the arctangent of x cubed plus the sine of x cubed, and remember your x's are in, your angles are in radians, that function, we want to find the area underneath that curve from 0 to 2, from 0 to 0.2. And we want it correct, incidentally, within 5 decimal places. Within 5 decimal places. So what you can do, of course, is, well, you know, if you look at the table, and let me just, this here, this is I made this table up, okay, where it has the Taylor series formula, and then it has some important Maclaurin series with some intervals of convergence. So the table 1 in the textbook from section 8.7 has radius of convergence, but I have my table where I have interval of convergence for some problems. And how many would be interested in having a copy of this document here? Okay, Felicity Wood, okay, I'm taking Kahindi, okay, let me make a note here. What I can do is in the course content folder, for section 8.7, I can put this document in for you to download, okay? And I probably won't be able to get to that till tomorrow, but I will get to it. And but for now, you know, you can use table 1 in section 8.7. But all right, no problem. We'll get that. I'll make sure you get an electronic copy of that in Blackboard under course content. And so we have the functions arctangent of x cubed and the sine of x cubed. Do you see the arctangent of x cubed or the sine of x cubed anywhere in this table? Do you see it anywhere in the table? Here's the power series for the arctangent function. Here's the power series for the sine function. Okay, Michael says a simplified version. Okay, so what Michael's saying, really, and I think I understand what Michael's saying. You have angles here, right? The sine of x. X is an angle. But if you wanted the sine of x cubed, couldn't you just replace the x with x cubed? And of course, it'll generate a new power series. You have to, wherever you see the x, you'd have to replace the x with x cubed. But you know, x is just an angle. It's an angle. So if x cubed is your angle, replace x with x cubed. Is that what you mean, Michael? Is that what you were? Okay, wonderful, wonderful. And the same with the arctangent of x. Okay, the arctangent of x is given here. The power series is there. But if I want the arctangent of x cubed, I'll just replace the x in the power series formula with x cubed. All right, so let me go to the solution and show you that, okay? So for our solution, okay, here's the power series for the arctangent of x. Okay, so the arctangent of x cubed, then I substitute x cubed for x, and I get this power series. But then, of course, I'm going to reduce the power series. I'm not going to have x cubed to the 2n plus 1 power. I'm gonna take the exponents and multiply them, because I'm raising x cubed to the 2n plus 1 power. So 2n plus 1 times 3 is 6n plus 3. Okay, and similarly, I can do the same thing with the sine of x, the power series for the sine of x. Here it is. So the sine of x cubed, I just substitute in x cubed for x, and I get the power series for the sine of x cubed. Okay, let me give you a moment to copy that down, but please let me know if you have any questions. Okay. Are there any questions before we move on to the next page here? All right. Well, if there are no questions, we'll move to the next page. So we have now established power series for the arctangent of x cubed and the sine of x cubed. So of course, I'm going to take those power series and substitute them in for the functions. Okay, that's what I do here. I substitute each of those power series in for the functions. And what I have to do is I have to get now the antiderivative of the power series. So I think you could have easily imagined that if I'm going to have the sum of two power series is a power series, and they both start at the same counter, n equals 0. So the sum of the two power series would be another power series, but the integral then of a power series should also be a power series, right? That would make sense. So what I do is I have the integral of a sum. I have the integral of a sum. The integral of a sum is the sum of the integrals. So that gets us down to the third step here. And I want to make sure I'm not going too fast. How many are kind of copying as we go along here? I think some of you do that. I understand, Mohammed. I understand. Let me know if you have any questions. All right, well now, let's look here at the integral of the power series. So, you know, it's an integral of a power series, right? Let me just erase here, hold on. This is an integral of a power series. The power series is a function of x, right? Power series is a function of x. So we're integrating with respect to x. But you know that the integral of a sum is the sum of the integrals. So I can write the integral of the power series as the sum of the integrals, which you see here. And I'm putting parentheses around things just so maybe you can, so it's totally clear to you. And this is the kind of work I would want to see for your final exam. You know, your final exam, you're going to have problems like this, and I would want to see this work. Okay. I need to see that you understand the concepts. So you can't go from this step, you know, down to this step, right? That would be works missing. Can't give full credit. Sometimes can't give any credit if work's missing, and you understand that. That you know, I need to assess your understanding of things. Okay, now I also the right hand side. No, Felicity, I would want to see every one of these steps. I can't imagine doing it without every one of these steps, really. To be honest, but I know that some of you think very nice. You know, you think well in your minds. But very good question, Felicity. Please, yes, show me all these steps, because then I really see that you understand. You know. Okay, now we need to do antiderivatives. So let's focus here. Let's focus here on this first integral here. Okay. What can I do with the -1 to the nth power and the 2n plus 1 in the denominator? Are those constants with respect to the integral? We know -1 to the nth power and 2n plus 1 power are not constants with respect to the power series because n changes. But with respect to the integral, that's right, Mohammed, -1 to the nth power and 2 times n plus 1, those aren't functions of x. We're integrating with respect to x. So -1 to the nth power divided by 2n plus 1 can be brought out in front of the integral. Similarly, for the second power series, very good. The second power series, the -1 to the nth power and 2 times the quantity 2n plus 1 factorial, that can be brought out in front of that integral. And so you're left with this then. Now you can get the antiderivatives. The antiderivative of 6n plus 3 would be just 6n plus 4, x to the 6n plus 4. Sorry, the antiderivative of x to the 6n plus third power, you know, it's one power more, so that would be x to the 6n plus 4 divided by 6n plus 4. And now you have written your integral, and of course you have constants of integration, C1 and C2, which combine to equal to C, but constant C. But you have now have this power series here with the constant of integration is the antiderivative of the arctangent of x cubed plus the sine of x cubed. That's what it is. It is the antiderivative. Okay, I'll give you a moment before I go to the next page. Okay, so what we want to do now is this, we have these two power series, right? What do you want to do with the two power series? What does your intuition tell you to do with these two power series that both start at the same starting point, n equals 0? What does your intuition tell you that you might want to do with those power series to simplify things a little bit? What's sort of a natural thing to do? So Felicity, that's right. We're going to combine the constants. Can we combine the power series? Can we add the power series together? Could we write the sum of the power series as just one power series? Can we write the sum of these two separate power series as one power series? Would that be possible? Sure. They both start, that's right, Michael, that's right, Felicity. They both start at n equals 0. They have the same starting point. Now, if the index were different, if like the second power series had an index of n equals 1, then you could just combine them together. But they both start at n equals 0. They go to infinity. And so you can rewrite this power series, the sum of the two power series, as this one power series. And like Felicity's suggestion, combine the constants, C1 and C2, I'll call it C1 plus C2 equal to C, and that gets me this power series. Okay, I'll give you a moment to copy that down. Okay, so now we're down to here. And this is a factorial here, 2n plus 1 quantity factorial here. Yep. But then this here is just 2n plus 1. Right, this is a factorial here. Yep. No problem, Mohammed. Are there any other good questions? So the common factor, of course, was x to the 6n plus 4 over 6 times n plus 4. We just factored that out, and we get this result. All right, are we ready to move to the next page? All right, well, now we have a formula. We have a formula. We have our antiderivative as a nice power series. So now what we want to do is compute the definite integral. Now the integral, by the way, the limits go from 0 to 0.2, and that's okay, because those limits fall within the interval of convergence for the power series of the arctangent of x cubed and the sine of x cubed. So that's okay. We can work with that. All right, and so now we're doing the definite integral. And of course, putting 0 in for x would just give us 0. So what I'm trying to say is, like, of course, as you know, when you compute a definite integral, you have to put the top limit and the bottom limit in. And here I put in the top limit, and there's a minus where I then got to put in the bottom limit. But if x equals 0, when I put 0 in for x, the whole power series is just 0. Okay. So that gets us down to here. Trying to take my time, trying to make sure everybody's comfortable. If I were in a classroom, of course, I'd be looking at you directly, right, in the class. And of course here, with if everybody had their webcams on, I could look at you all, and I'd turn mine on too, but it seems students are a little shy about using their webcams. So, you know, I don't want to, that's fine. So now what we do is we start evaluating this series now. But we have to remember we have a -1 to the nth power. That makes this series, what kind of series when you have a -1 to the nth power? What kind of series is it then? An alternating series. Good, Kahindi. Hence, we have to think about the alternating series estimation theorem. So if we're, one moment. Okay, so if we're going to be correct to 5 decimal places, that means that we have to keep computing terms of the series until we reach a series that's going to be less than 5 over 10 to the 6th power, right? Because 5 decimal places, 5 plus 1 is 6. So it turns out that, you know, the first term is going to be 0.00080. Well, that's greater than 5 over 10 to the 6th power, which is, let me see, that's 5 millions, right? That's greater than 5 millions. But the next term, okay, the next term, I mean, so like, you know, this was when n was equal to 0. That was the first term. Second term is when n equals 1. I'm substituting in a 1 for n. And there, that term is going to be 0.00000, hold on, 0.00000000512. That's less than 5 over 10 to the 6th power. So by the alternating series estimation theorem, how many terms of the series do we need to estimate this definite integral so that our answer is correct to within 5 decimal places? How many terms of the series do we need? Do we need 1 or do we need 2? That's right. Good, Michael. 1 term. And incidentally now, you know, when you do these problems, you should, for your homework, you should be practicing, you know, doing this. You're justifying when it's time to stop with the terms. On your final exam, I would expect to see this justification. Okay, okay, that's part of showing your work. Okay. I mean, how do you know when to stop adding terms? You know when the term of your series, when you reach a term that's less than 5 over 10 to the 6th power. Okay, so that's how you know. And I need to know how you know. So that's why I need to see this work, right? I care. I want to see that you understand. So, okay, may I move to the next page? Are there any questions? Okay. Well then, by the alternating series estimation theorem, the definite integral, the value will be approximately equal to just the first term of the series, 0.2 to the fourth power over 4 times 2, which is 0.00080. That's correct to 5 decimal places. And it's actually even correct to 7 decimal places, since the second term is less than 5 over 10 to the 8th power. We actually got even better accuracy than was asked for. All right, let me give you a moment to copy that down. Let me know if there are any questions. Okay, and we'll look at one more example here, so that, you know, we will look at one more example. But you are learning some of the most beautiful math there is here. You really are. And it's very applicable. Okay, very applicable. We could program a computer with these power series to do, you know, definite integrals that we can't do, you know, work out by hand. It's always best if you can work it out by hand. But, you know, and this was why, you know, but sometimes you can't work an integral out by hand because you don't have an antiderivative. And this is why mathematicians, you know, hundreds of years ago came up with these procedures. Because, you know, they needed answers and they had to develop the math to help them get the answers. I mean, it's really an amazing topic. Okay, let's go to the next example. Okay, something you can do with power series is you can multiply 2 power series together. Okay, so let me give you a moment to copy this example down. And I'll just mention again that in the textbook, in example 7, they show, by the way, how to find a Taylor series centered at a equals pi over 3 for the sine of x. And I recommend, I mean, I think you'll need to look at example 7 because we've been, you know, well, we've been looking at Maclaurin's series, and I'm doing a variety of different problems. Taylor series is but Maclaurin's series are centered about a equals 0. Well, example 7 shows you a power series. A Maclaurin series is a Taylor series centered about a equals 0. In example 7, you have a Taylor series centered about a equals pi over 3. So I'm going to ask you to go ahead and look at that example on your own. Okay? So, okay, so we have here a function that consists of the product of e to the 2x and the log of 1 plus x squared. Okay? And we want to find the first 3 non-zero terms in the Maclaurin series for that function. Okay, if you look in the table in the book, you'll see a Maclaurin series for e to the x, an exponential function, and you'll see a Maclaurin series for the log of 1 plus x. And that means we can get Maclaurin series for e to the 2x and the log of 1 plus x squared. But you don't see a Maclaurin series for the product of the exponential function e to the 2x times the log of 1 plus x squared. So but what you can do is you can find the power series for e to the 2x and the log of 1 plus x squared and multiply the power series together. So again, I think we can move to the next page now. We have this table here, table 1 from section 8.7. Okay, and once again, I'll make a link to my handout with the important Maclaurin series. I'll make a link to that in the course content folder in Black for section 8.7. All right, so we're going to utilize the log of 1 plus x. We're going to utilize e to the x. We're going to utilize, these power series. So, of course, for e to the 2x, we're going to substitute in 2x for x for the power series here for e to the x. And for the log of 1 plus x squared, we'll substitute x squared in for the power series for the log of 1 plus x. When we do so, this is what we're going to get. Now what I'm doing is I'm writing out, rather than write down the complete new power series with the summation notation, okay, I know you like the summation notation, but it's going to serve us better writing out the first 3 or 4 terms of each of the power series. I mean, back in the table, that's what you have, right? They write out some terms of the power series here. And all you're going to do is write those terms out, but you're going to substitute 2x for x here. Everywhere you see the x. And for e to the x. And then x squared for the log of 1 plus x. So this would be what you have. This power series times this power series. See the big multiplication symbol there? And then what I do is I reduce each power series. Okay. And then we have to find the first 3 non-zero terms of the product of this power of these power series. So I know, like, for instance, the 1, I mean, I can distribute the 1 times x squared. and I can distribute the 1 times negative x squared to the 4th. I mean, what I'm saying is to multiply one power series by another, I can take each term of the first power series, each term, and distribute it. I can separately take each term of the first power series and then distribute it to every term in the second power series. Okay, and when I do that, like I'll have a 1 times x squared. That's fine. And I'll have a 1 times negative x to the 4th over 2. And I could keep going, right? I could keep going. But remember, they only want the first 3 non-zero terms of the power series. So I don't maybe need to worry about x to the, like I could go 1 times x to the 6th power over 3, but I may not need to worry about that. Okay, and in fact I don't, because the 2x times x squared is going to give me 2x times x squared. That's going to give me a 3rd degree power. Okay, and let me see here. What I'm trying to do is I'm trying to justify how I got both of these terms here, 2x times x squared and 2x squared times x. Okay, yeah, I can take 2x and multiply it by that x squared. But I can also take the 2x squared in the first power series and multiply it by x squared. And that's going to get me 2x to the 4th power. See, I have to worry. The first 3 non-zero terms are going to be an x squared term, an x cubed term, and an x to the 4th term. Okay, and I've accounted for all of those. I've accounted for all of those now, and so these are my first 3 terms of the power series. Okay, let me give you a moment to copy that. Okay, are there any questions at all regarding this example? And I know that you'll have to watch. I mean, it's, you know, it takes time to feel comfortable, but hopefully. Tina says, I don't know how you got the last line, the first 3 terms. Okay, so, so x squared, 1 times x squared gives me the x squared. And then I have a 2x, let me see, let me put this, maybe use different colors here. Then I have 2x squared times x squared. That gets me 2x cubed. And then I'm going to have the negative 1 times negative x squared over 1 times negative x to the 4th over 2 plus 2x to the 4th that's going to add up to 3/2 x to the 4th. And then any other terms are going to be of higher power. Okay, I mean, obviously, I just have the first 3 terms. The product of the Maclaurin series is going to be an infinite power series. But I've just written out the first 3 terms. Very good, Tina. Good question. Okay, are there any other good questions? All right, I'll